All right. Okay. Do you have any questions before we start? Oh boy, how'd you feel about that one?
I felt great until I got out and realized that the capacitor was still connected to the battery, and I saw that it was not.
Oh, that question. God, sorry.
The take home and the example had it connected to the battery or disconnected from the battery. No, they were no.
One of them had it connected, the other one didn't. And in this case, it was connected. Well, all the magnitudes will be the same, so hopefully he'll be okay with that to an extent. If he's not, I will be angry at him, but I can't fix that.
The first only that was the first one. The second one was the energy, and the third one was whether or not the tractor was or
Okay.
I got the fourth part wrong. I don't know.
Yeah, it's a repulsive force regardless of whether it's connected to the battery or not, I believe. It's been a hot minute. But anyway, do you have questions about ODE before I go straight into first order stuff?
All I have to say, I haven't really studied this.
That's okay. Then I'll just brush y'all up on the basic methods of solving first order differential equations. As soon as I can type a new share, probably I'll get these additional practice problems. Yes, and the lecture notes with class meetings and find some first order problems. Wow, this one's. So I'm going to use a whiteboard to derive the general solution to a linear first order differential equation and show you how to do it in case that's something you ever need to do. So I will just, this may be helpful. We will find out. But suppose we have y prime of t plus y prime, I'm going to make it easy. P t y equals g t. Oh, perfect. Hi, yes, we're moving here. Please put on a mask if you do not have one. COVID cases are up to 50 apparently, so they're asking that we all mask indoors.
No, they're not getting us.
Yeah, they haven't been telling us weekly. But I'm just going to, in case some of you are able to get, like, I'm going to show you how to derive the formula for first order linear differential equations, but at the end I'll just tell you what to memorize. That I find that the deriving is sometimes helpful enough. And at least if you understand the derivation, you'll understand why it looks the way it does. I'll give you the equation right now. The equation is actually mu t gt dt plus c all over mu t, where mu t equals e to the pt dt. Some of you may be wondering, where did the negative sign go? The negative sign only appears if g of t is 0. But if g of t is 0, you observe that this whole thing goes away. So you're just left with c over mu of t. And if mu of t is e to whatever and it's in the denominator, it gets a negative sign. So I prefer just memorizing this. But in order to, does anyone have any questions about this equation? I use it for all first order linear differential equations. Okay, so the quick derivation, if you are in a pickle, is to multiply everything by the function mu of t. So we have mu y prime plus mu p y equals mu g. Now you may observe there's the mu g term up there that we were seeing before. So where is it going to come from? If mu p equals mu prime, then this can be written mu y prime plus mu prime y. Now, why did we do this? Do any of you remember from way back when? Why we want a mu prime here? It's the product rule. Mu y prime is equal to what? Take mu prime y plus mu y prime. The product rule, that allows us to turn this thing into mu y prime equals mu g. And now if you just take the integral of both sides, right, then you get mu y equals the integral of mu t gt dt. plus c. And then you can divide both sides by mu. And so this is how you get the formula. But the formula is right here for memorization, for first order. We're practicing first order. So this is the general formula. And if you just plug everything into this equation, it'll all work out. You can use this differential equation to solve for mu of t by writing p equals mu prime over mu, which gives you integral p dt equals ln mu. The integral of this is ln mu, which there's a use substitution reason for that, but I think it's less important. You already remember what mu of t is because you've done it a million times. So this is our equation. And it's also right up here for the general solution to a first order linear differential equation. With the particular solution here, and the what's it called? The homogeneous solution here. Any questions about this equation? We'll do a problem with it in a second. And by second, I mean now. As soon as I find it. Why not this one? This one looks not too bad. I mean, they all look bad. But they're not. I think everything is going to work out just terrible. We'll do this one. I don't know which one to do. I'm so sad. I have no idea which one will be working here. But surely one of them will. Hello, Jesse. Please wear a mask if you can. We have masks. We're doing first order equations, linear equations, just reviewing. Where did my whiteboard go? What happened to, oh, this pages. Anyway, so we rewrote the general equation for first order linear differential equations right here. Is it readable? Is this fine? Okay, great. All right, then we'll do the practice problem right now, and I'm gonna just write it down on the board and have y'all take a sec to try and solve it. Hopefully my pluses and my t's look sufficiently different from each other. Now, I don't know if she made this easy or not. She might have made it excessively difficult. But do recall that you need to put it into standard form before you can use this equation. Standard form requires no coefficient in front of y prime. Divide all by t. Y, I forgot the y here. And then, of course, I'll write the formula up here, and y'all can play with it. Mu of t is equal to e to the integral pt dt. And, huh? What? Oh, you don't like writing it?
No, I don't.
It's going to be t plus, e to the t squared over 2 times 2, which is e to the t squared. And when you multiply e to the t squared over to the right, it disappears. Just watch. Start doing it, and everything is going to work out just fine. And then once someone's done getting mu of t, please let me know what it is. I will also do it, obviously, but I want to hear if anyone else.
Wait, so there is or there is not a negative either in the middle?
No negative, as long as you use the general formula, mu g dt plus c over mu.
Okay, but you don't use the general formula.
Which you would only do if this was equal to 0. Then you would simply write y equals mu t plus c, where mu equals e to the negative pt dt. But that's a crazy extra thing to memorize if g equals 0. So I simply prefer to memorize this and plug in mu and always get the right answer, if that makes sense. But you can also memorize if g equals 0. Let me make this g clearer. If g equals 0, then y equals mu of t plus c, where mu is equal to e to the negative pt. So mu is equal to, does anyone have an idea yet?
It's actually t. times t to the squared.
It's yes, it's t e to the t squared. Now you may be wondering, why is that? Because it's e to the integral of 1 over t plus 2t dt, which is e to the ln t plus t squared, which is equal to e to the ln t e to the t squared, which is equal to t e to the t squared. So you have mu t, yay. And now you may also be wondering, how on earth are we supposed to integrate this? Well, the good thing is that we don't need to integrate this. We integrate mu times g. So now it is time to plug everything into this formula and let me know what y'all get. Everything is going to work out wonderfully. It's going to be lovely.
Did you say, I think, at the end said what question you were
So there's going to be stuff from obviously what we just learned in class, and then there's going to be, you need to be able to solve any question from exam 2 and exam 1, she said. But I believe in class she said something about there being a second order question where you can choose any method, and a second order question where you must use only a specific method. Which one? Who knows? So you'd probably better learn all of them. But we'll practice those at length tomorrow. And then Wednesday, we'll probably do one final brush up of all the last stuff. And of course, this is all going to be recorded. So, because it's being recorded right now. How exciting. I'm going to start plugging things in. T e to the t squared times t squared e to the negative t squared. And you can immediately see how this all becomes very lovely. Because e to the t squared times e to the negative t squared is what? E to the 0, which is 1. Agree? Everyone, yes? Happy? Lovely. So it's just t cubed dt plus c over t e to the t squared, which is equal to t to the 4th over 4 plus c all over t e to the t squared, which gives us t cubed e to the negative t squared over 4 plus e to the c e to the negative t squared over t. You may be wondering, where did all that come from? Well, I just divided this term by this guy and put the e to the t squared in the numerator, and divided this term by this guy and put the e to the t squared in the numerator. Let me check if that's right. We're going to find out. Yay! Oh, she didn't even put it in. What a waste. Oh, that's so dumb. Well, there you go. E to the t squared. It's in the denominator if you want it to be. Either way works. Any questions about this problem?
Where did the DT come from?
The dt problem. What do you mean? This is an integral. This is the general formula for linear differential equations, first order differential equations. Mu is this, g is this. Well, in standard form, it's this. And then that's it. Yep. And this formula works for all first order linear differential equations. There are other types of first order differential equations that we will now also review, but this formula is the one for the linear ones. And it's the one that you'll need to use in the case that you're doing like reduction of order. If she tells you to do reduction of order, you're probably going to have a first order differential equation, and it's probably going to look ugly, and you're going to have to use this formula if you do a reduction of order problem. So we'll probably do a reduction of order problem on Tuesday. And again, it'll be recorded because we can't make it. So anyway, unless I can't do it on Zoom, but I'll try my absolute darndest to. Any questions about this problem? No? Okay, let's see. What else is there to remind y'all about? Stop. No, angry. I want to this. As a prospective student. Okay, I must stop share for a second because it keeps getting in my way. Okay, so types of, oh, there's separable equations. Oh, there's so many types. I forgot how many types there are. We only have an hour. What are we gonna do?
We'll be very involved with this.
We should probably do Bernoulli real quick.
Oh, is that the one if greater than 1 or 0?
If you have y to the r on the right side and r is greater than 1, then you need to use this substitution, and then everything works out again. Ultimately, a lot of first order differential equations and second order differential equations is using the appropriate substitution and then plugging and chugging. A lot of it ends up being very straightforward as long as you remember the substitution to make. If you memorize that this substitution is what you should do for a Bernoulli equation, and then you plug it in, everything kind of just works out. As long as you figure out what du dt is and replace y prime with all of that, one of the classic things you have to do in substitution is get the right derivative and plug that in. So I don't know if we'll practice this one or we'll do another one. We'll save this for later. Separable equations are easy too. You've done these a million trillion times. They're just, do you recall separable equations?
Is it possible to separate the equation?
Yeah, if it's possible to separate the equation into factors entirely of x and factors entirely of y, where there's no x plus y or whatever, and then you can't multiply out, then you can get an equation where it's an integral with y, and an equation where it's an integral with x, and everything is happy and lovely. Like this equation, for example, has a factor entirely of x that we can stick the dx on the right. And then this equation, if we put 2xy squared on the right, can be split into negative 2x and y squared. Oh, I'm not sharing screen. I should have done that. So separable differential equations, as long as you can split it into factors that are all x and y on the right side and the left. Looks like you can apparently do it for this insane one as well. How lovely. I don't think you could integrate it, but you could certainly pretend to. And then, this one by grouping, I don't know if she'll give you a crazy one like this. Also, probably not very easy to integrate. It'll be fine. Anyway. Oh, that for boundary. Yeah, I mean, initial value. Y'all are fine with initial value problems at this point, right? Just plug in the condition once you're done. Homogeneous equations. Yes. Do y'all want to practice homogeneous for interesting? You just need to have the right plugging. I remember teaching a formula for this that makes it fairly easy to check. So we'll do a homogeneous problem right now, and maybe later we'll do something separable. Separable. No, this one's separable, but not homogeneous. This one's homogeneous. Why is it homogeneous? Why is this problem homogeneous? No. If you can plug in alpha x and alpha y into every x and y, and all the alphas cancel out in the end, then it's a homogeneous equation. Now, a quicker way you can spot it, though, is if all the added terms in the numerator and denominator have orders of 3. And by orders of 3, I mean xy squared has an order of 3. And x cubed has an order of 3, and y cubed has an order of 3. If every single term in numerator and denominator has the same order, then it's probably going to be homogeneous. And that's like a quick way to intuitively check. Everyone's like, Jonah, how would I know to do the alpha thing? And I suggest doing the alpha thing if you see that all the terms in the numerator and denominator are of the same order, counting both variables. Because then when you perform this substitution, alpha x and alpha y, and the equation doesn't change, it's homogeneous. And then you have to simply do a nice little substitution. And my preferred substitution is u equals y over x. The reason for this is that it's easier to determine what y prime is. So we'll do a problem right now, and I'll show you how to use that substitution. So we're going to share the whiteboard. And we'll go for this problem, y prime. Maybe I'll use a different color. I'm tired of pink now. Maroon. I loved using all the different colors. In whiteboard for circuits, I never do that. So we have y prime equals y cubed plus x cubed over xy squared. And now we will begin the substitution. U equals y over x. The first thing to do is ignore the way this substitution looks because it's done. Instead, we're going to rewrite it as ux equals y. Why would I do that? Does anyone have any idea why I like this more? The product rule for taking the derivative. Yes, that's incorrectly understood. But so we will take the derivative of both sides in order to find out what y prime is. And of course, the derivative of ux is u prime x plus ux prime. Now, if you're wondering, Jonan, what is x prime? Remember that we're taking the derivative with respect to x or t or whatever the dependent variable is in such an equation. So x prime is just 1. I'll cross that out. And this is equal to y prime. So y prime equals u prime x plus u. And now we can plug all of these things in here. Can everyone see the monitor, by the way? Is my head in the way? Okay. Huh? Because we're taking the derivative of x with respect to x. So this prime is d dx. I should make clear.
Oh, God.
That may, yeah. Because x here is the dependent variable. We just chosen it to be. Yeah. Sound good? Sorry. Okay. So now we have this y prime equals u prime x plus u. X prime is equal to 1 because dx is 1. And we'll plug everything in to get u prime x plus u equals u cubed x cubed plus x cubed over u squared x cubed. Let me know if everyone agrees with the crazy thing I just did. You observe that y is equal to ux, and so y squared is u squared x squared. So here we have u squared x cubed in the denominator, and something lovely happens. All of these x's cancel out to become u cubed plus 1 over u squared. Is this really lovely? I don't know, but we'll find out. So we have u prime x plus u equals u cubed plus 1 over u squared. Now, a helpful hint is to remember that homogeneous equations are supposed to be able to turn into separable equations. So we need to somehow rearrange this so that we have a bunch of u stuff multiplied by a bunch of x stuff. Does anyone have an idea of the first step to take to do so?
The thing that I want to do is divide out the u squared on the right side, and then you can get rid of the u because you just subtract the u from both sides, and that would take care of the whole variable.
That sounds clever. We can totally do that. If the denominator were more complicated, you would probably want to take u over to the right side here and then right, make it common denominator. If the denominator here were crazy complicated, and you had this u still here on the right, you'd want to take it over to the other side, right? And then make it common denominator with respect to u. So this is u cubed over u squared, and you have a bunch of u stuff, and it's still separable, right? So this is still separable, but Tyler was right. We can make things a lot quicker. We'll note that this becomes 1 over u squared, by the way. But we can make things, so this is one way of getting a separable equation. U prime x equals 1 over u squared. Quite nice. But our other way, as Tyler suggested, is to divide everything by u squared here. So this is an aside. This is what you would do if you had a more complicated denominator. Take the u to the other side, make common denominator, combine, and then you have a separable equation. We have a simpler thing here, so we can write this as u prime x plus u equals u plus 1 over u squared. So u prime x equals 1 over u squared, which you'll observe is the same thing. We can write u prime as du dx and perform the separation, which requires us to put all the u's here and the dx and x's here to get u squared du equals dx over x. And this gives us u cubed over 3 equals ln x plus c. And then we just plug in u we get y cubed over 3x cubed equals ln x plus c. So y equals the cube root of 3x cubed ln x plus c 3x cubed. Now I know I really skipped a bunch of steps there, but does it make sense that this is the answer? I will just not skip steps because, yeah, I'm going to stop skipping steps. We'll go up further to get y cubed equals 3x cubed ln x plus 3c x cubed. Of course, we can absorb the 3 away into c and write this as y equals the cube root of 3x cubed ln x plus cx cubed. Funny enough, we can also pull out x cubed. Why did I even do that? What did I, yet another way we can do this is to cube both sides. We get y over the cube root of 3 times x equals the cube root of ln x plus c. This is nice because now x is on the outside here. So we have y equals x cube root 3 ln x plus 3c, or just c. So those are like a million ways to write the answer. But does everyone get the basic substitution u equals y over x? And then ux prime, y prime equals u prime x plus u.
Just plug it in for y prime.
Yeah, you kind of just plug it in for y prime and then you solve. So you're done. Now this crazy bit is just making it separable because a homogeneous equation, once you plug in this substitution, will turn into a separable equation, which is the strange, confusing, who knows how that happens or why. It's the clever bit, basically. Usually, I actually have a hunch. The reason it turns into a separable equation is because of all of these x's, all of these y's will turn into x's, and then some other thing. And so all of the x's in the numerator and denominator end up canceling out, no matter what, if it's a homogeneous equation. And then you just have a u thing on the right, and you have this on the left, and you can combine the u here with what's here on the right. And then you have all u's on the right, and then multiplication stuff on the left, and so you can separate it. I wonder if I should make like a step-by-step way of thinking about that. I don't know. No, it's too complicated because it might look different some other time, but just plug and chug and then solve until you get a separable equation. And then you should be fine. We can do another one another time if that helps, but that's homogeneous. And we share.
Just u y divided by x.
U equals y over x. Sometimes you can use the other form, but that's silly. I mean, it's not, but I really don't see why you would. So, because the derivativing doesn't work as well. Maybe some clever mathematician can come up with some reason to use it, like in a pickle, but I don't know how many actual pickles occur. But let us see what else there is in first order to check, because we have about another 30 minutes. I think there are some other weird stuff. Oh, there's the phase diagrams. Didn't want to do those. Spinel. Oh, autonomous equations, right? So this is, can you tell, so we'll do a quick like quiz. Can you tell what kind of differential equation this one is? How can we solve it? Does anyone disagree, agree? Agrees. Okay, what about this one?
I'm gonna say separable.
Tyler Malley thinks separable. Anyone agree or disagree? Good, this one's separable as well. Are we just in the separable page? Ah, we are. Oh no, it's about existence and uniqueness. But all of those just so happen to be separable equations, which is nice. And they're not even that bad to integrate. Let's see. This one is apparently homogeneous. It doesn't apply as well to the trick I told you about checking the orders of the numerator and the denominator. So you really do have to plug in the alpha thing just to check. one way intuitively that I might be able to tell that it's homogeneous is because the square roots of x squared and y squared have an order of 1. And so if you plug in, so that means this has an order of 1, this has an order of 1, this has an order of 1, this has an order of 1. Every single term in the numerators has the order of 1. So it also looks like it might be homogeneous. So that's a way to just look and be like, maybe. You can't check until you do. You can't know for sure until you plug in this x alpha x thing, whatever, and check if all the alphas go away. But that is one way to intuitively decide whether or not to perform that check. Now, it's been a hot minute since autonomous equations, but autonomous equations are a thing you can do a graph for. Ooh, I don't know if she's going to put any of these on the exam, but phase diagrams were a thing that some of you may recall with displeasure or enjoyment. But the idea is that if a function looks like this and only depends on the y that you start with, so your initial value, different initial values will cause the function to behave different ways. And there are certain critical values which will cause the function to just be a line forever. Where if, for example, f of y equals 0, that means the slope of y with respect to time is 0. So if you start from a certain y, you'll remain at that y for all of time. So just looking at this equation, we can, this is an autonomous equation because of the way we can think about it. Because we can look at it as, because the slope depends entirely on your initial value for y, you can understand how such an equation works by choosing different values of y and seeing what the function looks like after that. So let's look at some examples here. Yeah, it might show up again in the exam 3. So the main thing that she'll want you to do is write a phase portrait and a phase line. Let's look at the phase line first because it'll help us understand the phase portrait. The first thing we need to do is find critical points. So I remind you that if you plug in a certain y, such as 0, and it turns this whole thing into 0, then the slope dy dt is 0, which means that if your initial point of your differential equation is y equals 0, then your equation will never change as time passes. As t increases, dy dt is 0, so the change in y is 0. So you just stay 0 forever.
So every critical point will be this. I mean, if graph, it will be this straight line. That
straight line. So you can see those lines in this, because this actually is a bit of a helpful point, is to look at these elements of the graph. You see the green, you see the green, you see the blue. Those are our 3 critical points for this problem. The points at which, if you started there, you would never leave. But these critical points can be either stable or unstable. Whether or not they are stable depends on the derivative dy dt outside of the critical points. If the derivative outside of the critical points tends to lead you back to the critical point, then you have a stable critical point. But if your derivative outside of your critical point leads you away from it, then you have an unstable critical point. So we can look at what we mean by that. Let's actually look at this one in particular. So we have our critical point, like let's pick 1. So that's this critical point right here. If we get a number greater than 1, let's say we have 1.5, as our initial value, the first point of our function, y equals 1.5. Well, let's plug it in here. This becomes a negative factor, and this becomes a positive factor, right? So this whole slope is negative. That means that if you have y equals 1, and you go a little bit higher, your slope from then on is going to be downward, approaching the critical point again. It's not going to pass the critical point because the slope of the critical point is 0, right? So it's just got to slowly taper out. And that's why you can see this graph here tapering out toward 0, toward 1. Does that kind of make sense? So we can look right below 1 as well. We can pick something like 0.9. We observe that this is positive and this is positive. So our slope is positive. So just underneath 1, our slope is a positive slope that leads us back to 1. If our initial y value was something like 0.9, we would be pulled upward as time approaches back to the critical point y equals 1. So that we go back to that equilibrium solution. And that is why this is called asymptotically stable because any solutions just outside of the critical point will tend back toward the critical point. And so understanding the phase portrait is simply a matter of like understanding how the initial value affects the slope of the function starting after that initial value. Does that kind of make sense? Yes, okay, great. So let's look briefly at the zero term here. At zero, we can look above and below zero. Above zero, we have a positive term and a positive term, agree? So our slope is positive, which means that if you're just above zero and you start just above zero, the slope will pull you up away from zero, agree? Okay, so what if we're below zero? Does it make sense that you're gonna go down? Looking at the equations, that's something for you to review for yourself. Look at the equation, imagine a number between 0 and 1 that's close to 0, and decide for yourself whether or not this makes sense, that if you start from a number just below 0, you'll go down away from 0.
So it slopes up when you're reaching the critical point, and it slopes down when it's reaching downwards.
It depends on the critical point. When we plugged in numbers around 1, our slope pulled us down or up toward 1. So if we went slightly away from 1, like because of some random perturbation, so you can imagine this as an actual system. Some random perturbation pulled your height or whatever, your potential energy away from the electron, whatever, away from the critical point, the center where it likes to be. It gets pulled back in.
I mean, any number, I mean, when you're going to go up, if everything's above 1, so it's going downward.
Everything above 1 results in a downward slope, which takes you back down to 1. So, but at 0, it's different. Everything above 0 results in an upward slope. And so it takes you away from 0. Below 0, we can plug in random numbers in our head. Something below 0 is negative, so we have a negative number here. But something below 0 slightly isn't enough to make this term negative, so this is a positive term. So we have in total a negative slope. So we're pulled away from 0. But our asymptote, so our asymptote is kind of backwards, like way back in time, it's attached to 0. But as you leave 0, you go down. But then you slant back to this new critical point, -1. So that's why we have these two types, our asymptotically stable critical point, where the derivative, and this is the clever bit, this is why the phase line is so quick and easy, is that this arrow right here represents the slope between 0 and 1, the derivative, excuse me. This arrow represents the derivative above 1, whether it's positive or negative. And this arrow represents the derivative below negative. And so you can simply plug numbers into your equation to determine these arrows. And then you can draw your phase portrait based on those numbers. I don't know, we have 22 minutes, so we could do, did I say autonomous equations can be graphed? They can be given a phase portrait, where you can know basically the way that any solution will behave. So we are basically graphing it. This is pretty much close to graphing it. So we will do a problem, I guess. Oh, exact equations. I missed those. Why didn't she put any additional problems here?
What happened was on exam 1, she said, "What do you guys want? What other support do you guys want to see from me?" And I put down practice problems along with one other people. So she started it with the next unit.
Oh, so she made this for the first time ever. That's so cool. It's so useful, I think. I mean, I think it's useful. I've been using it this whole time. Well, I guess then we will just, I'll just come up with one. Why not? Let me share a whiteboard. We will have, and the equation, oh, how do I delete this page? Oh, well, we'll have the equation in green. Y dy dt, so the slope of y, this function t, is simply a function of f of y minus 3, y, I don't know, plus 3. So step 1, critical points. I'll give you steps. derivatives above and below. Let me put y here as well, so we have 3. Derivatives above and below. Wait, this is identical to the other problem. Sorry, I'm changing it again. Y minus 5. Now we're done. Sorry. I apologize. I've changed it slightly. Derivatives above and below, phase line, and finally phase portrait. So step 1, critical points. What are the critical points?
3, 5, and 0.
Okay, so we will, those are critical points. So it's probably good to set up the phase line now. So I'll make my phase line a little black line. And I'll put 3 critical points on, 0, 3, and 5. So just starting with our phase line. And we want to figure out the derivatives above and below. So below 0, what do we suppose that the derivative is, negative or positive? Below 0. This is negative, and this is negative. So 3 negatives makes it negative. Okay, so I'll put a little blue arrow downward. So we can already tell that this is probably an unstable point, but we'll see what happens between. So between, I should label this with black, 0, 3, and 5. Okay, between 0 and 3, what is the slope? Tyler says positive. What does anybody else think? What is the slope going to be? James also says, wait, James. Okay. Aaron, why do you think negative? Well, we can plug it in here we can plug in a random number here to find out. Yeah. So we can plug in something like 1 and we can find out. 1 minus 3 is negative. 1 minus 5 is negative. Y is positive. Positive. Negative, negative, positive. So dy dt, the slope is going to be positive. It's going to increase. Is that going to make sense, Aaron? All right. Do you want to tell us, do you want to try and figure out what the slope between 5 and 3 is?
So if you plug in any random number like 4.
We can plug in 4.
So positive, negative, and positive.
Okay.
So therefore negative goes down.
Perfect. Okay. And then anyone got 5? Above 5? Positive. Okay. So now it's time to classify these points. Is 0 asymptotically stable or unstable? Unstable. What about 3? Asymptotically stable. I don't know if it'll ever not be asymptotically stable. I don't know what it is. Semi-stable. Okay, I didn't remember. Thank you so much for telling. Yeah, so the semi-stable is the other possible type. And then finally, this one is, of course, unstable. We are now ready to draw our phase portraits. That's our next step here. Boop, 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 boop. Yeah, you want to draw kind of low because you don't need a lot of negatives. You hardly need any because there's no critical point that's below 0. So we just need a bit of space below 0 to draw stuff. So let me draw, we need to draw a line for 3 and a line for 5. 5, 3, and 0. And this is our y-axis. This is our t-axis. If you have an unstable critical point, your asymptote is in the past. Asymptote is in the past. So you start with an asymptote from the past that leaves 0 quickly, more quickly over time. And if you're asked, so again, on the other side, we also have an asymptote in the past, but it doesn't go like that because if it's a stable point, you have an asymptote in the future. So we have a future asymptote for 3 and a past asymptote for 0. So we can join these with an inflection point, just like that. Agree so far? Everything good? Great. Does this make sense as a drawing to everyone?
So one is faster. What's the other one?
This one leaves 0 increasingly quickly because it never slows down like this, like because the 0.3 here forces the slope to slow down to 0 over time. So it has to have this inflection point. But underneath the 0, there's no stable point. So there's nothing really to force the slope to go back down to 0. So it can just go down indefinitely. So let's look at above 3. 3 has what, a future asymptote or a past asymptote? 3, well, it's asymptotically stable. So your line is going to go down to 3. So what I mean by future asymptote is that your equation, your solution has to go toward 3 over time. So eventually in the future, it's going to fall down to the level of 3 if you're between 3 and 5. Now, if the critical point 5 is unstable, that means if you start from 5, you'll eventually leave 5. So we can imagine that once upon a time it started at 5, but it eventually goes away from 5. That's what I mean by past asymptote. In the past, we may have been close to 5, but we must leave 5 if so. In the future, we'll be close to 3 because 3 is a stable point. You get sucked toward it, while 5 pushes you away. So here above 5, here above 5, in the past, you may have been close to 5. But if you were, you would get flung away. And that concludes our phase portrait. Any questions on the steps to develop a phase portrait?
So the path starts from the left.
Yeah.
Right.
Yeah. And intuitively, hopefully these have like they make sense just like from the idea of the equation. If it's unstable, it means that if you were near that point, you would eventually go away from it. So we talk about having started nearby and then escaping from the unstable points. And so that's why both up here and down here, they both escape to infinity. While in the middle, they do escape 5, but they go to 3. And they escape 0 and they get sucked into 3. And you can kind of read that from these arrows. These arrows tell you where a point's going to go. Up, down. All right. Any questions before we move on to exact equations, which will be our last material for today? Okay. So exact equations are fun. I like exact equations. The reason exact equations are cool is because of some clever facts about partial derivatives. You've all taken calculus 3, so you know partial derivatives. And you may recall that if a function has the partial derivative yx, that happens to be equal to its partial derivative xy. So we can do a clever trick. If you have a function, if you have a differential equation that looks like this, we have f xy dx plus, I don't know, g xy dy, and that all equals 0. This equation is an exact differential equation if fy equals gx. Now let's think about the reason and what we mean by exact differential equation. If fy equals gx, there exists some phi. So this backwards e represents there exists. If some of you have taken discrete math, you may recall this. This means there exists some function phi such that phi x equals f and phi y equals g. And then you can integrate away from g and f to get phi. And that's true if fy equals gx. And the reason for this now, so let's assume for the sake of discussion that in fact phi does exist. We can rewrite this entire equation as phi x dx plus phi y dy. And of course, if this function phi really exists, phi xy would have to equal phi yx. So fy must equal gx because of partial derivatives. So you can check if a situation is exact, if it looks kind of like this, and fy equals gx. And you may be wondering, okay, why y? It's the one that's opposite to x. Yx is the one that's opposite to y. So you can look at the actual like one with y and one with the x. Now she may cause it to look like this: f, xy plus g xy y dy dx equals 0. In that case, you can put it back into this standard form by performing what operation? What would you do to put this into standard form? By what? Dx. And if you multiply by dx, you get it back to look like this. If she did dx dy somewhere, you just multiply by dy to repair everything. So that's how you could put it back into exact form. But in order to check whether it's exact, you still have to perform fy equals gx. Let's check right here.
She might also pull the case in where she'll pick a k term on one of those, and you have to solve it so that you have f of y equals.
Oh, so you have to pick the k that makes this true, and then you have to integrate. Okay, so that's another clever bit. Interesting. I didn't know that she did that. Thank you for letting me know. Oh, you have a friend who remembers. Good.
Exams are right here.
Ah, oh, right there. Like all nice, just for review. Okay, so we have 8 minutes, so I'm going to show you what to do, because the main thing trips some people up is the integration. Basically, the idea is to integrate both of them and then combine, like make sure that. Okay, do y'all remember prime factorization? Here, this is an analogy. 1/8 plus 1/6. What is the common denominator of 8 and 6? No.
24.
24. Why is it only 24?
I would have just done trial and error.
Oh, right. Never mind. Okay. Well, it happens to be trial and error because of the way that you prime factorize. You write 2 times 2 times 2, 2 times 3. And you only pick one of the two 2's that are in the pair. And then you combine, you take all the others. So the common denominator is 2, and then times 2 times 2 times 3, which is equal to 24. When you are trying to find common denominators and you have a pair of similar prime factors, you only need one of the two items in the pair to figure out the total common denominator. If you picked both items in the pair, then you would have an extra 2 here and you get 48, which is too much. And so I will show you that analogy will matter later. Just keep it, you can see, so keep it out of your head for a bit while we do a problem that I will now locate. We will stay slightly longer if we need to, because I mean, I just have to get back in time for my shift at 3 p.m. and to nap preferably. But do we do this absolutely insane one, or do we do this other app? So, or this, I don't know. Wow, we love this, don't we? There's probably a clever way to do this. That's really nice. Why not? Let's take one from the exam. Because I'm sure she won't. She gives you the really difficult ones in the problems, so you really get it. But we don't have time for a really difficult one. So we'll do a simple one instead. Are there any in the exam?
There was only supposed to be one, but there was a second one you also solved with that. So this is the kind of complicated one.
Okay. I guess we should do the more complicated one. But it's not insanely complicated, so that's why we'll do it. So I will remind you of the steps. Step 1, check exact. Okay, we'll put it in standard form for exact. And I'll write down the equation in a bit. Step 2, check exactness. And I'll show you these steps one by one. Integrate both terms. And compare. All right, so I will show you how to do this. Compare and C equals phi, I believe. That's our final solution. Okay, so our problem here is a different color, kxy plus e to the x sine y plus 2y plus x squared plus e to the x cosine y dy dx is equal to 0. This is not in standard form, so we have to do step 1. Put it in standard form by multiplying everything by dx. So kxy plus e to the x sine y dx plus 2y plus x squared plus e to the x cosine y dy equals 0. Now we check exactness. To check exactness, you take the partial derivative with respect to y of the x term and the partial derivative with respect to x of the y term. The partial derivative with respect to y of this term here is kx plus e to the x cosine y. Agree? The partial derivative of this term with respect to x is 2x plus e to the x cosine y. Are these equal? Once k equals 2, they are. So we write that k equals 2 to make this exact. So now we need to rewrite the terms and integrate them both. So let me rewrite, and then I'll put an arrow that shows you what to integrate next. So we'll write 2xy plus e to the x sine y dx. So you plugged in our k, the k that makes it work, plus 2y plus x squared plus e to the x cosine y dy. The x term we integrate with respect to x. And the y term we integrate with respect to y. So you can see it's kind of flipped. So the first term integrates to x squared y plus e to the x sine y. The second term integrates to y squared plus x squared y plus e to the x sine y. Question?
How come the k became 2?
Because we needed the k that would make this equation exact.
Oh,
It is exact if k equals 2. Do you see? Exactness occurs if these two things equal each other. So on the left side here, this integrates to, if you integrate x squared, you get x squared y plus e to the x sine y. If you integrate y on the right side here, you get y squared plus x squared y plus e to the x sine y. And so finally, the question is compare. How do we make the left side and the right side equal? That probably doesn't make a lot of sense because it doesn't really seem like we can do that. But basically, when we integrate with respect to x, there is a secret term here. We shall call it h of y. Because the derivative of h of y with respect to x is 0, right? And so it would, when if you're trying to get some function phi, because we're trying to get a function phi, whose derivative with respect to x is this, and whose derivative with respect to y is this, then that function phi has an x and a y in it. And we don't know what that is yet. But both of these give us pieces of the puzzle. and we basically combine all the pieces of the puzzle together. So the final answer is almost ready. We have phi x of y is simply equal to the compared full term, y squared plus x squared y plus e to the x sine y. We don't write 2x squared y or 2e to the x sine y. We're not adding them together. We're looking at them and comparing them until we figure out what the term that gave us both this guy and this guy was. We can even look at this. We can take the derivative of this with respect to x, and you see that we get 2xy plus e to the x sine y, which is this guy right here. And if we take the derivative of this with respect to y, we get 2y plus x squared plus e to the x cosine y, which is right here. So we were looking for phi. Phi is the function that we got when we integrated this with respect to x and this with respect to y. And finally, our solution is phi equals c. And you can just plug it all in if you want. But that is the answer to an exact differential equation.
Oh, I didn't know the finding the k is that simple.
Yeah, it's just look at the left side and the right side and see what k will make this equal. Yes. So that's exact differential equations. It's been a hot minute since you did this. Hopefully this was helpful practice. So I hope hopefully the steps help. You can probably do some of the examples in the homework. And hopefully the integration isn't too crazy. It's usually nice because you're really not integrating with respect to two different variables. So you didn't have to do an integration of parts for this, which is really nice. You didn't have to do any integration by parts. You just had to only integrate one of the two because you're either integrating by x or by y, which makes it quicker and easier than something that looks absolutely insane. So we can actually just briefly look back at one of these problems and observe that if we were trying to integrate this with respect to x, for example, all we would care about is e to the x. And if we were trying to integrate this with respect to y, all we would care about is 3y squared, because e to the x plus 1 has nothing to do with y. So the integration of this problem isn't as insane as we thought it was. This one is a little bit worse. And I will show you, I will give you an idea of how to not die in case this becomes, something that you have to deal with. So suppose that you were trying to integrate this by x. You would have to deal with this e to the x squared term and integrate that. And that would be absolutely insane. And you probably wouldn't want to do that. However, if you take the right side here and integrate it with respect to y, you can observe that it's pretty easy, right? Because you're just integrating y, it becomes y squared over 2, et cetera, et cetera. What you do is you take what you get and you take the derivative of that with respect to x. And you compare it and you see if you need anything else. And if you don't, you're done. I wish I had the time to show you, but I do not. But if you want to try to, basically ignore this guy. Just take the integral of the right side with respect to y, and then take the derivative of that with respect to x. And check if you already have all the requisite terms. And if you don't, add another term that fixes it. And if you do that, then you have phi, because phi is a function whose derivative with respect to x is this, and whose derivative with respect to y is this. So that's how you can ignore insane looking things like this. Thank you for coming to my TED Talk. Anyway, no problem. I'll hopefully see some of you tomorrow. I will, of course, try to Zoom it and record it if I can get a room. If not, I will just only Zoom it, probably, most likely, and not do it in any room at all, which is probably the better idea, honestly. So yeah, have a great day.
Thank you, Jonan.
No problem. It was good to see you, Sam. Hopefully this was helpful to an extent.
Yes, it was. Let me know if you'll do Zoom tomorrow.
I will try my darndest to do Zoom.
Okay. Are you leaning more towards just like doing it on Zoom entirely?
I'm leaning towards doing it on Zoom entirely if I can't get a room. If I get a room to do Zoom in, I will do Zoom.
Okay.
Because the goal is to do it in Zoom no matter what. It will happen on Zoom.
Okay.
But it'll happen on Zoom either in a physical room or no physical room.
Okay.
And preferably it'll happen in a physical room.
Okay. Okay, sweet. Okay, I'll see you tomorrow. Thank
All right,
you.
bye, Sam. Have a great day.
Bye. Here.